As you go through your Maths A level, differentiation is a concept that's going to come up time and time again in some different ways, but these are the principles on which it will all be based. Now, let us say that you had a y or a function equals some amount of x to a power, so ax to the power of b. Now, the symbol for differentiation, if you're using y, is dy over dx, or if it's a function, you'll add an apostrophe between the f and the brackets. In the event of differentiating, what happens is you take your coefficient and you times it by the power, so you end up with ab. And then, for your x, you take one away from the power. So for instance, if you had y equals 2x cubed, dy over dx would be, so 2 times 3 is 6, and then 3 minus 1 is 2. If you were to differentiate that again, you'd have 6 times 2 is 12, and then that drops to x to the power of 1, or just x. To keep on going, just to show what happens, if we were to do 12 times 1, that'll be 12, but then the x would come to the power of 0. Now anything to the power of 0 is 1, so 12 times 1, just 12. The x disappears. And finally, if you have a number on its own, again imagining that like x to the 0, 12 times 0 is 0. Doesn't then matter that x should go to x to the power of minus 1. The coefficient is 0 times by 0, it is nothing. If you have a whole number, it just disappears. Now, the proper function of differentiation, why it's helpful, will be explored in later videos. Just to say for now, it's to do with working out the gradients of curves, say, well, if they're not straight lines, you can't use a y equals mx plus c. You want to know, based on the equation, what the gradient of the curve is at a very specific point, so that you can work out maybe a tangent. It doesn't have to always be a curve, maybe it's some kind of scenario-based thing, like the rate at which water is pouring out of a tap. That comes under modelling differentiation. Again, that'll be covered in its own right. For now, we're just going to be looking at the basic algebra side of things, and we'll apply later. As we go through this then, we are just going to be using these same kind of concepts over and over again, just times coefficient and the power in front, and then take one away from the power. There are a couple of things we may want to bear in mind though, some places where we may get tripped up. That's where we have some unusual indices, some unusual powers. For instance, if we had a number over x, well, if x is in the denominator, then we can say that's the same as ax, and then to the minus power of whatever power it had here. And similarly here, if the x, because it's in the denominator, will be to the minus 1. Now, if there's another coefficient to x down in the denominator, it doesn't get brought up like this with a negative power. You just keep it as numerator divided by whatever that denominator coefficient was. So a over bx is like a over b times x to the minus 1. Just to give some other more numerical examples like I did above, let's say that we had 7 over x squared. That would be the same as 7x to the minus 2. If we had 3 over 4x to the power of 8, that would be the same as 3 over 4x to the power of minus 8. When it comes to differentiating, we want to be certain of what the power is when we're firstly timesing by that coefficient and then taking one away from that power. Just looking at this in fraction form may not be absolutely clear, so we'll always suggest rewriting it as such. In a similar vein, if you have a root, whether it's a square root or a cube root or any higher root, that's just the same as x to a fractional power where this type of root here goes in the denominator. So if it was a square root, it would be a half. If it's a cube root, it's a third. Here, because you now have a root of bx, because b is underneath the root with the x, it does get included this time in our rewriting. So it's the bx in its entirety to the power of 1 over a. For a number-based example, if, yes, again, you had the cube root of just x, that would be x to the 1 over 3. If we had the sixth root of 5x squared, again, everything underneath is still being applied to that, so still 5x squared to the power of 1/6. If you actually wanted to expand that, you do the coefficient whole number just to that power. You can either leave it as 5 to the power of 6 if you want, or you can work out a value. And then here, if you have a power, bracket another power, that's just like timesing these two together. Well, 2 times a 6 is 2 over 6, which simplifies to 1 over 3. So this could be 5 to the 6th times x to the 3rd, if you so wished. If we actually go on to a real example then, this here on the right may look a little horrific, but that's just because I want to demonstrate the different ways we can take this. Here we have a fraction. If we were asked to differentiate this right now, there is a way that you can differentiate fractions as they are. That is in A2, and we'll be covering again, that's a different facet of differentiation we'll deal with in another video. Here, just to simplify, we'll want to work out what this numerator is if you do divide through by the denominator. Here then, if we want to do that, it's probably best that we rewrite this denominator. If x times square root of x can be written as x times x to the power of a half, based on what was down here, then we can call that in turn x to the 3 over 2. What we have is x times x to the power. If it's the same letter times together, you just add the powers. So essentially the power of 1 add the power of a half is 3 over 2. Now for the dividing, that's going the opposite way. When we times, we added the powers, dividing will minus. Here you now have 9x divided by x to the 3 over 2. So for our first term, that becomes 9x, that's currently a power of 1, and from that we'll minus our 3 over 2. We'll simplify that in a second. The next term, you just end up with 3 divided by your x root x. There's no x term, it's just on the top, it's as simple as that. You can write that as x to the power of 3 over 2 if you want on the denominator, it's up to you. And then finally at the end, we have minus x to the minus 1 minus 3 over 2. Simplifying this, we get y is 9x to the minus a half plus 3. Actually, at this point I will write it as minus 3 over 2. And then here minus x to the minus 5 over 2. Remember, at this stage we still only have y. We've only been rewriting. It's at this stage that we're going to do our dy over dx to differentiate. So 9 times minus a half is going to be minus 9 over 2. You could say 4.5, I'll keep in fractions. X to the minus 3 over 2. Because we're taking 1 away from minus a half is minus 1.5. Next, 3 times minus 3 over 2, it's going to be minus 9 over 2 again. And that now, however, is going to drop to minus 5 over 2. And then here, minus 1 essentially times minus 5 over 2. Minus times a minus is now a plus. And that's just going to be 5 over 2, followed by x. Now to take 1 away from that, you're now left with minus 7 over 2. It's a lot of fractions, but I just want to see that is something that you could do. They're probably not going to give you that many fractions, but it's possible. You'd need to know how to deal with it. If we're okay with that, just the idea of first of all wanting to simplify anything that's a little more complex, and then being able to do these differentiation steps, the coefficient times the power, minus 1 from the power, let's see how you can get along with a question of your own. Given here that the function x is defined by 8x brackets 5 plus x squared minus 1 over x to the 5. I'd like you to work out what the actual value of the differentiated function of 1 is. Pause the video, have a go at this for yourself, think about the principles we've already been talking about, then press play when you're ready to compare. Okay, so first of all, again, we're going to want to simplify. It's not a fraction this time, but we can still do something. We can expand the brackets. Just like with the fraction, you will eventually get to a point where you can deal with things that are multiplied together. But right now, to start off with, let's just get rid of the brackets. 8x times 5 is going to be 40x. 8x times x squared is going to be 8x cubed. And 8x times minus 1 over x to the 5. So that would be 8x over x to the 5. But due to how fractions are going to cancel, this x up here is going to cancel with one of the x's on the denominator, leaving that as now just 8 over x to the 4, which in turn we can say is the same as 8x to the minus 4. Now, differentiating this, you're going to have, well, if this is a power of 1 here, 40 times 1 is 40. And then that 1 drops to a 0, so the x term disappears, which is 40. Here, we'd have 8 times 3. That's going to be 24. And I'll write x for the moment, but we'll replace that with a 1. This power then gets dropped to 2. Then here, minus 8 times minus 4 is going to be a positive 32. And then that's now an x, again we'll place in a second. That drops to minus 5. I keep saying we're going to replace with 1. Well, that's what we do with functions. Whatever you have in the bracket, the letter, in this case x, gets replaced by that. So we'll have 40 plus 24, 1 squared, plus 32 times 1 to the power of minus 5. If you put that into your calculator, you should get a value of 96. If we're okay with this, let's move on and see what an actual paper question would look like. So, here we're told that y equals x squared minus k root x, where k is a constant. And from this, we're to find what dy over dx is. So here we can see that you can have some unknowns in these questions that we'll have to solve for. Still, we'll start off in the usual way. We may want to rewrite the square root into actual power. So we get y equals x squared minus kx to the half. Now differentiating this, dy over dx, you get coefficient of 1 times 2 is just 2. And then x, the 2 power drops to a power of 1, so it's just x. And here, minus k times a half, which is minus a half k. And x here, the power drops to minus a half. This, for your first part of the question, is your dy over dx. Second part of the question, though, is saying that given that y is decreasing at x equals 4, find the set of possible values for k. As I already alluded to earlier, this differentiation can be used to work out the gradients of curves at specific points. So in this case, when we're saying that y is decreasing, we're saying as x is going along, y is going down, So ultimately you have some kind of negative gradient. If the dy over dx is giving you the gradient then, and if it's decreasing, that means that your dy over dx is a negative number. It's less than 0. This expression then, we can just set up in an inequality. So half k to the x power minus a half. This is less than 0. From this stage, we're just going to be looking at some rearranging. So because the letter we're trying to make the subject we're trying to solve for is currently a negative, we'll add it over. So 2x is less than a half k. Actually, I'll just write that as over the square root of x at this stage, or rather 2x is less than k over 2 root x, because if you have a fraction in the numerator, you can bring the denominator down to join the real denominator. Here then, if you're wanting to get the k on its own, you'll want to bring up the new denominator, because we don't want our k being divided by anything. The way you bring it up is to times, so you end up with 4x root x. We know that x is 4, so you've got 4 lots of 4 times the square root of 4 is less than k. Well, 4 times 4 is 16. The square root of 4 is 2. 16 times 2 is 32. So, the gradient of this curve will be negative. Y will be decreasing at x is 4, so long as this k value here is greater than 32.